Okay, so today probably be pretty short for you guys. I'd initially planned to finish up filling in our notes on parent functions, but I've decided, and then going on to something else. I think we're just going to finish this up, and I'll give you the rest of the period to work on the assignment that goes with it, so you can get that out of the way. And then next time we'll come back and we'll talk about how we can transform these things. But rather than pile too much stuff on at once, I think we'll just kind of wrap this up and give you a chance to do the practice on it. Okay, so if we go back to last time we met, remember we were talking about parent functions, right? We had a couple definitions. A family of graphs is a collection of graphs that all display similar characteristics. Well, a parent function is just the simplest member of that family of graphs, right? It's the most basic form of each of these different types of functions, right? And we filled in most of these. I think we just have two left. Looking at the assignment, it asks you to enter domains and ranges and things like that. It asks you to always enter those using interval notation. So I want to take a second and just go back and let's add, for any answers that aren't already in interval notation for our notes, let's go back and rewrite those using interval notation. So then you can use this document. I'll immediately put these notes up when we're done, so you can access it through your Google Classroom, and then the information is right there. So if that way, you can pull that up in one window and do the assignment in the other window if necessary. So when we say all reals for the domain and the range, we all know what that means in terms of the graph, right? It means that the projection of the graph covers the entire x-axis, or if we project it onto the y-axis, it covers the entire y-axis. In other words, there's no place the ant couldn't go. There's no x or y value the ant couldn't get to. So we can just say all real. If we want to write that using interval notation, just remember how that works. That just means it goes all the way from negative infinity up to positive infinity. Okay? And so same thing for absolute value here. The domain is all reals. The range wasn't, and we already wrote that using interval notation. Okay, but there's the domain of the absolute value function in interval notation. Quadratic, domain was all reals again. Range was not, but for cubic, both the domain and the range were all reals. Oh boy, this pen. Square root. Okay, we had the domain and the range. Both of those we wrote in interval notation. Cube root, all reals for both the domain and the range. And reciprocal function. Okay, this was a weird one, right? The domain was just every x value except 0, and the range was every x value except every y value except 0, right? This is the easiest way to say that, but if we have to write it using interval notation, we could write it like this. We could write it as, it's going to be two intervals, right? Because the x values, we have to stop at 0 because 0 is not included. So we would have all values of x less than 0, and that's how we'd say that, right? Or all values of x greater than 0. So it'd look like that, wouldn't it? Okay. And then same thing for the range, right? All the y values from negative infinity to 0, but we need parentheses because we're not including 0, and then parentheses 0, comma, infinity. Okay. Does that make sense? Give me 1 to 5 real quick. Is that making sense what I'm doing? Okay. Good. All right. Okay, so in other words, I just added to the domain and the range on all these. I just added how we would write those in interval notation if it asked for interval notation. Okay. All right, so here's where we ended up. We had two more functions to do, exponential function and logarithmic function. Okay, so exponential function, we're specifically going to pick the exponential function with a base of 2. So that looks like this. F of x equals 2 to the x. Now that's a weird function. That's different than what we're used to. We're used to seeing things like when we have an exponent, we're used to seeing things like this, where we have a variable as our base and a constant number as our exponent, right? Like in the quadratic or the cubic parent functions. An exponential function flips that around. In an exponential function, you have a constant number as the base, and it's the variable goes in the exponent. Okay, so this is one where we could make a t-table on this to figure out some key points. Okay, there's a weird one here though. Let's start with 0 like we often do. Start in the middle with 0. If x is 0, then y equals 2 to the 0. Does anybody remember from Algebra 1 the zero exponent property, sometimes called the zero power property? If I take any number other than 0, any non-zero number to the 0 power, what does that equal? Yeah, it equals 1. It equals 1. It's a weird one, okay? And we'll talk more about that. We're going to review our properties of exponents, in a little while. When we get into polynomials, we start doing polynomials, we'll review properties of exponents, and I'll go through and I'll tell you why it works that way. But for now, just believe me. Okay, it equals 1. So we get a point at 0, 1, and every exponential function is going to have, that point is going to be on the graph. Okay, and then if we pick some other values, well, like if I plug in, let's say we plug in like 3, for example, right? Well, how about if I plug in 1? In this case, if I plug in 1, 2 to the 1 is just equal to 2, right? So in this case, it would go through the point 1, 2. If the base were 10, then it would go through the point 1, 10, right? So the different bases are going to give you different points there, but the behavior is going to be essentially the same. If I put in a really big number, like what if I put in something like 2 to the, well, this isn't even that big. What if I put in something like 2 to the 8th? So I'm going to let x equal 8, and my output would be 2 to the 8th. Well, 2 to the 8th is 256. So it grows pretty fast, doesn't it? Right? You can see that this function starts to really explode upward. Right? It's going to go up very, very fast. Well, what if I take a negative number? Like what if I take something like, let's do negative 8. Whoops. What if I do negative 8? Then the output is 2 to the negative 8. Does anybody remember this property? If I have a negative exponent, how could I write that as with a positive exponent? How could I rewrite that expression, 2 to the negative 8? How could I write that using a positive exponent? Where does the power go? A negative exponent in the numerator ends up being a positive exponent where? Do you remember this stuff from Algebra 1? You may not. That's okay. It's been a long time. In the denominator. 2 to the negative 8 is the same as 1 over 2 to the positive 8. So an easy way to remember that is a negative exponent on top equals corresponds to a positive exponent on the bottom. So that would be 1 over 256. That's a really small number, right? It's a small, small fraction. And so we can see what this behavior is going to be, right? For small or for negative values of x, as we move further to the left, the numbers just get smaller and smaller and smaller, and they end up being very, very tiny fractions, right? They get closer and closer and closer to 0. So the function, it has an asymptote, like some of the functions we looked at the other day, right? That's what an exponential function looks like. you can see that it starts off for negative values of x, it's growing very slowly. But as soon as x starts to become positive, it really grows quickly. And you've probably heard the expression when something is really exploding, it's growing, explosively, it's just taking off. You say, oh man, that's growing exponentially, right? We just say that all the time. Well, this is why, because an exponential function grows so quickly, right? It's the function that grows extremely rapidly when x is positive. Okay, so that's what it looks like. It goes through the point 0, 1. What's the domain on this one? Just type it in chat. What's the domain of an exponential function? Yeah, it's all reals, isn't it? How do I say that using interval notation? Type it in chat for me, everybody. There we go. Good. Yeah, in parentheses, negative infinity to infinity. Good. Okay, what's the range? What's the range? What are the y values? We want the set of all the y values on that represented on that graph. Well, look, there's an asymptote, isn't there? Let's add our asymptote. That helps to add the asymptote here. There's an asymptote on the x-axis, right? Well, it's the x-axis, so that's just the line y equals 0. That's the equation of our horizontal asymptote on the x-axis. Remember what an asymptote is. An asymptote is just a line that a function approaches but never gets to, right? So this function, as the ant walks forever to the left towards negative infinity, towards an x value of negative infinity, that the graph is just deflected towards the x-axis, but it never gets there. So what's the domain then? Type the domain in for me, please, in chat. Oh, okay, I'm seeing it. Yeah, there it is. Good. So the domain is 0 to infinity, and I have to have parentheses there, right? Because y never gets to 0. Y is only greater than 0. It never actually gets to 0, right? Okay. I did the analogy the other day with the door? Did I talk about walking towards? Okay, good. Yeah. So remember that behavior. So what about our end behavior here? Let's look at the ends of this thing. As x approaches infinity, so as the ant goes infinitely far to the right, where does the function carry him? Towards what y value? What does f of x approach there? As x approaches infinity, f of x approaches what? Yeah, good, infinity. It goes up forever, doesn't it? Okay. What about at the other end? So the ant can walk infinitely far to the left as well. As x approaches negative infinity. Now think about this one. What y value does the ant approach as he goes infinitely far to the left? Type that in. Oh, you guys are getting this. Yeah, it's 0, isn't it? Good. Okay. And pretty clearly this is continuous, isn't it? Because I can graph the whole thing without ever picking my pen off the board. Okay. I have to have a lot of ink to do that because it's infinite, but I could do it without ever picking my pen off the board. Okay, the last one is pretty strange. The logarithmic function. Okay, and we're going to do a natural logarithmic function, which just means that our base of our logarithm, and this is going to sound really strange to you, and don't worry about it. This is, we may not get to this even this year. We'll see. So the base is the natural number e, which is just like pi. It's a naturally occurring constant like pi. We know is 3.14159, blah, 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 right? The natural number is 2. I think it's 7128, blah, 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 something like that. Okay, it's just kind of like a pi-ish number. But we could have the base be 10 or 2 or anything. If we choose the base to be e, that's the one we usually choose in math and science, then here's how we write the logarithmic function. We write it as, that's an ln. That's like a cursive ln. So the natural log of x. There are other kinds of logs, though. I could do something like this. Like I could do, sometimes you'll see it written like this. That means a base 10 log, if I write it that way. I don't want to get into too much detail on this because the point is they all look and behave the same. They're all going to look and behave the same. They're all going to go through the point 1, 0. And logarithms behave the opposite of exponential functions. In fact, they're inverses of each other. We'll talk more about that later in the year. So instead of starting off growing very slowly and ending up growing very quickly as the ant walks from left to right, they do the precise opposite. They start off growing extremely quickly and they end up growing very slowly. Okay? They also have asymptotic behavior, but instead of a horizontal asymptote on the x-axis, logarithmic functions have a vertical asymptote on the y-axis. So the equation of the asymptote is the vertical line x equals 0. Okay? That's all we need to know, is that that's how they behave. Okay? So what's the domain then of this logarithmic function? Type it in chat for me, please. What's the domain of that? What's the set of all the x values that the ant could ever step on? Yeah, it's 0 to infinity, isn't it? Right? And we need parentheses there, don't we? Because it can never get to an x value of 0. Okay? What about the range? Now, even though this function, the log function, grows ever more slowly, it's always growing. It's always growing. So as you go to the right, it continues to grow. So what do you think? What's the range on this thing? Everybody type it in. Okay, good. It's all reals, isn't it? Negative infinity to infinity. Because the function extends. If the ant walks to the left, he's going to get deflected down forever. As he walks to the right, he's going to go up forever, just slowly is all. So if we wrote that with interval notation, we just write it like this, right? Okay, end behavior. Well, the ant can walk to the right forever. As x approaches infinity, what does f of x approach? Where does the function carry the ant vertically when he goes to the right forever? Okay, that's fine, Savannah. I got you. Yeah, infinity, right? It's going up forever. So as x approaches infinity, f of x, or y, approaches infinity. Now, on the other side, we're kind of stuck. The ant runs into this wall at the asymptote. He can't go, he's stopped. He can't go to the left forever. He can't even get to 0, but he can approach 0. As x approaches 0, what does f of x or y approach? And look what's happening here. As the ant walks towards 0, he's just deflected down, right? Okay, good. Negative infinity. Good. And clearly, this is another one that I could graph this without ever picking my pen off the board. So it's continuous. Okay? All right, you got it all there. I will quickly make a PDF of these notes and put it up. I'll show you where it'll go. If you go to classwork and you go to instructional notes and you go to unit 3, it's going to be the one right here that says parent functions. Okay, the one that says not transforming parent functions, that's for next time. It'll be the one that just says parent functions. I'm gonna replace the one that's there with, I think ours is a little bit better. The notes for our period are a little bit better. So I'm going to replace the one that says P4 with P7, and then that'll be the one to use. Okay. You may have at it. You can work on assignment 3.2, practice 1. I'm here if you have questions, so just work away, and I'll probably even let you go a few minutes early. Okay. But go ahead and just work on it in the classroom, and I'm here to answer your questions if you have any.
How do you type a cube root into Desmos? I was trying to figure it out.
Okay, good question. Let's look and see. So on Desmos, whoops, good question. On Desmos, I'll show you how. On Desmos, you can do this. I think you can do it 2 ways. So one thing I can do is if I type out, nope, that's not it. I can type, I think it's CB. Yeah, if I type CBRT, it's a pretty slick way to do it. If I type SQRT, it makes a square root. If I type CBRT, it makes a cube root. Okay, you don't have to do it that way though. You can also go down here to the bottom to the keyboard. You can get everything off of the keyboard. If I go down to the keyboard, there's a square root. If I want a cube root, I go over to functions, miscellaneous, and it's right there. I can do a radical where I can put any number I want on the radical. So I can make it a cube root or a fourth root or anything, right? If I choose that little button, I can make that a 3 and then hit the left arrow and put something inside. But it's easier just to type CBRT. Okay? I'll make a note of that in our notes. Okay? I'll add a little page where I remind you guys about that. I'll put it in our notes.